Cooling with dehumidifying. During a simple cooling process, the specific humidity will remain constant while the relative humidity increases. The air with high relative humidity can be troublesome and it will cause unwanted problems. Therefore, we are going to remove some of the moisture content so that we can reach within the comfortable humidity. In other words, we are going to dehumidify the air. The humidification process requires cooling the air below its dew point temperature, where we want to promote condensation. Once the condensation begins, part of the moisture will be removed from the air. After these processes, the air will be cool and saturated. Note that the condensate temperature is normally equal to the air exit temperature. If we look at the psychometric chart for cooling and dehumidifying process, air at state 1 having 30 degrees Celsius for the dry bulb temperature and the relative humidity is 80%. The air will be cool until it reaches saturation line. Note that saturation line means the relative humidity is 100%. The air will then further cool until it reaches our desired temperature of 14 degrees Celsius. This portion representing the condensation. At state 2, the relative humidity will be 100%. This is what it means by the result from this process will be saturated and cool. The moisture removal is represented by the specific humidity. The specific humidity at state 2 will be lesser than specific humidity at state 1. We know that specific humidity is the ratio between moisture content with the dry air, and usually the content for the dry air is constant. This will be the schematic diagram for cooling and dehumidification. There will be cooling coils which going to absorb the heat from our channel. As the air passes through the cooling coil, at some portion the air will start to condensate. The condensation water will drop into the condensate pan. It will then remove from our system. Note that the value for the condensate water temperature is the same with the temperature of the air leaving our channel. Next, we are going to perform the mass balance and energy balance analysis. For the mass balance of the dry air, the mass flow rate of the dry air at the inlet is equal to the mass flow rate of the dry air at the outlet. Thus, we can denote it as m.a. For the mass balance of the water or vapor, from the conservation of mass, we will have this expression. The mass flow rate of the water vapor for the air entering our system is equal to the mass flow rate of the water vapor for the air leaving our system plus with the mass flow rate of the condensation water. Now we are going to substitute m.v equal to m.a times omega. We can rearrange this expression to this equation. For the energy balance, we are going to get this expression. This term representing the energy of flowing air entering our system. This term representing the energy of flowing air leaving our system. This term representing the moisture content removed from our system. And this term representing the heat rejected from our system. We can rearrange the expression to this equation. Note that the enthalpy for the condensate water is equal to HF at the condensate temperature. This means you are going to refer to table A4.